Welcome to the session. In this session, we will discuss about Hall effect. Hall effect is the phenomenon in which a transverse voltage EH is developed across a semiconductor sample. Carrying current is kept perpendicular to the magnetic. What we mean to say is Hall effect arises only when we apply both electric field and magnetic field simultaneously and so let us deep down into the discussion. So first we have a semiconductor sample kept at the system. This is x-axis, this is y, and this is z-axis. So first, no electric field is applied, no magnetic field is applied to this semiconductor sample. So in the absence of both electric and magnetic field, the electrons and holes present in the sample will move randomly like gas particles. But if you apply only electric field, so here we are applying electric field E along x-axis, this side negative, this side positive. So when we apply electric field only, no magnetic field, only electric field only, both electrons and holes both will drift. So holes drifting towards negative terminal with the drift velocity of VDH, and electrons are drifting towards positive terminal velocity of VDE. So here VDE is the drift velocity for electrons, VDH is the drift velocity for holes. So here when we apply electric field, the current produced by the application of electric field is known as drift current. Only application of electric field is going to lead to the drift. So Jn, current density of electrons due to drift, is given by n number of electrons with their charge q and their velocity vde. So Jn drift is equal to nq vde. But velocity is proportional to applied electric field. V is equal to mu. So substituting vde. So what we are going to get the drift velocity as nq mu n dx. Similarly, if you go for Jp drift, dq vdh, dq v dx. So on applying electric field along x-axis and magnetic field vz along z-axis, that means we are applying electric field and magnetic field both simultaneously and to this semiconductor sample. And y direction is a open circuit. You know that current passes only in a closed circuit, so there should be no current flow along y direction. But as a result of the crossed electric and magnetic field, particles, both electrons and holes, experience a Lorentz force Fl. So expression for Lorentz force Fl is equivalent to QV cross QV. QV is the electric field, QV is the magnetic field. So it can be written as Fl is equal to Q into V cross P. Now let us write this Lorentz force acting on electron. Lorentz force acting on electron is equal to charge of electron minus Q into velocity of electrons VDE along x-axis and x cap direction, and magnetic field is along z cap direction. So F is equal to Q VD x cap cross z cap. The cross product of x cross j is minus y direction. What does it mean? So the application of Lorentz force is pushing the electrons towards negative y direction. Actually, what is y? Is a open circuit, but application of this Lorentz force is making towards y direction. Right, Lorentz force acting on holes. Fh is equal to charge of the holes is Q, velocity of holes is VDH along x cap direction, and field Vz along z cap. So Fh is equal to VDH Bz x cap dash H. Again, the cross product of x cross J is minus y. So it means again these holes are also pushed in the negative. Actually, Y is open. There should be no current flow along y direction, but because of this Lorentz force, both electrons and holes are moving, right? So if some flow is taking place, means there must be some electric field acting along y direction. Field components EYE, that means electric field acting electrons along y direction. EYH for electrons and holes are set up by Lorentz force and calculate this. So the Fe, Lorentz force acting on electrons is equal to minus q into E by E, and Fh is equal to q into E by H. Comparing equation 1 and 2 with the equation 1 says, equation 1 is saying that F is equal to q VDE Bz. So comparing Ey is equivalent to q VDE Bz, Eyh is equal to minus q VDH Bz. These are the respectively electrical components acting along y direction. So because of this electric fields, the current density JYE and JYH are taking place along y direction. So now, since the oppositely charged electrons and holes are both reflected downwards, the current density is JYE and JYH will be in opposite directions. So let us write the expression for JYE. So JY is equal to sigma EY. So this sigma n is the conductivity of electrons, and naturally it is given by n. And so substituting that sigma n, Jy is equal to n q mu VDE Bz. Also we know that velocity is directly proportional to applied electric field. To remove the proportional symbol, we are introducing a coefficient mu n. So in the place of this VDE, we are going to keep this mu n. So Jy is equal to q place of VDE into P. So finally Jy expression is equal to nq million square Ex Vz. Similarly, if you write for JYH, sigma P into E by H, where sigma is equal to PQ mu P into Vz. So JYH is equal to minus PQ mu P square Ex Vz. In a steady state under open circuit conditions, there should be no current in that direction. Several times we are mentioning that there should be no current along y direction. So to avoid this unwanted current, the semiconductor sample internally developing field, opposing internal field, that opposing internal field we will call as Hall field EH, and this Hall field is going to balance this JY and JYH. That means the net direction currents due to will be compensated by or opposed by the Hall field, and this internally developed field we are going to call as Hall field. So sigma EH, here EH is the Hall field. Sigma EH is equivalent to JYE plus JY. Sigma EH is equal in magnitude, opposite in direction. So that negative sign indicates that this is opposing force. Sigma EH is equal to minus JY plus JY. From this, Hall field EH is equal to minus JYE plus JYH by sigma. And let us substitute the value of JYE and JYH. EH is equal to minus of the JYE value NQ million square X Vz, and what is the JYH value? Minus PQ mu P square X Vz by sigma. This sigma is sum of electron current and hole PQ. So multiplying with this negative sign, minus plus PQ mu P square minus NQ n square, and we are taking X Vz common by PQ mu NQ. Already we know that Jx is equal to sigma Ex. From this Ex can be written as Jx by sigma. So here we will replace this Ex with Jx by sigma. So what happens then? Ex is replaced with Jx by sigma. So PQ mu P square means square Jx by Bz into sigma sigma square. So finally the expression for all electric field, all voltage is equal to PQ square minus NQN square into JXPZ by PQ plus NQN square. If you define all coefficient is represented by H, and the all coefficient is a ratio between all field to applied electric. So what is the expression? RH is equal to all field EH to applied electromagnetic JXPZ. So substituting the all field value PQV square minus NQN square into JXPZ by PQV square plus NQN square whole JXPZ cancel. So the all coefficient value is equal to PQV square minus NQN square by PQV plus NQN square. Intrinsic semiconductor, we know that N is equal to P. So in the expression, if you substitute N is equal to P, what happens? The RH, because already what is the expression we have? RH is equal to Q mu P square minus NQ N square by PQ mu P plus NQ mu N. If N is equal to P, what happens? RH value is equal to 0. RH is equal to 0 is possible only N is equal to P, and this is the case for intrinsic semiconductor. Means whenever all coefficient we are getting neutral, it is indication of intrinsic semiconductor. For n-type semiconductor, we know that N is far greater than P. Ignoring the P terms, so what we are going to get NQ mu N square by N square Q square N square. So all coefficient is negative. Which kind of semiconductors? N-type semiconductors. All coefficient is going to be negative. And in the case of P-type semiconductor, we know that the holes are majority pairs, P is far greater than. Ignoring n terms in this expression, taking care of only P terms, PQ mu P square by P square Q square square. So PQ mu P, so RH is equal to 1 by P plus Q. So it is only possible for P-type semiconductor. And what are the applications of it? So by using this all coefficient, we can determine the nature of semiconductor. What does it mean by nature of semiconductor? See, we are going to find out based upon the sign combination of RH is equal to 0. See, RH is negative type, RH is positive for P. And by using this all effect, we can also determine the carrier concentration. That RH is equal to minus 1 by NQ. Send this N this side. N is equal to minus 1 by RH into Q. So the all coefficient and the charge of the electron, we are able to find out the carrier concentration of N as well as P. Can determine the mobility of carriers. We know that sigma is equal to N mu, is equal to sigma by N. But minus 1 by N we can return as RH. So U can be determined as indication of activity expression. So for the three applications of all effect is going to graph semiconductor is used to find out the concentration, and it is also used to